for review. So we will actually be starting with 5.2 officially, but I did want to look at those application problems at the end of this 5.1 section. So you can kind of see how this idea of solving a system of equation comes into play with applications. So let's take a look at this first example over here. This one is talking about at the Springfield Zoo, they have different admission prices for adults and children. So they're saying when Mr. and Mrs. Weaver went with their 5 children, they ended up paying $33. Mrs. Wong and her 3 children only paid $18.50. So the idea is, based on that, can we come up with what the adult ticket prices and the children's ticket prices will be? So in this case, as you can see, for the first part, they're telling us that it's Mr. and Mrs. Weaver. So of course, we know those are 2 adults with their 5 children. So the way you will set this up, we can kind of use, you can use X and Y as your 2 variables to represent the ticket prices for adult and children, or you can also use A to represent the ticket prices for the adults. And then we'll use C for the child's ticket price. So in this case, you actually have the equations given to you, when they're talking about Mr. and Mrs. Weaver. So that would be 2 adults, and then their 5 children, and they ended up paying a total of $33. Then they're telling us Mrs. Wong, so that was just 1 adult, and then she was with 3 children, and she ends up paying $18.50. So that's actually where you set up your system of equations from, just from that information that they have given you. Now, in this case, I would recommend using either the substitution or the addition method. It doesn't matter which one you go with. So since this one kind of has that A by itself over here, where your coefficient is 1, we can actually use substitution here. So that way you can kind of see how the substitution method works out one more time. So we'll use the substitution method here, which means we will need to rewrite our second equation to get A by itself, which means we want to move the 3C to the other side so that we can get A by itself. So of course, you would end up getting A equals, you can write it as 1850 minus 3C or negative 3C plus 1850, doesn't matter. So we're going to rewrite our second equation by getting A by itself on one side and moving everything else to the other side. So this will be our first equation. This will be our second equation. Now, the way substitution works is basically we are going to be taking this value, which is equal to A, and substitute that in our first equation for this variable over here. Okay? So we are literally going to take our second equation and put it into our first equation. Okay, so we've got 2 times A, and I'm going to leave that space blank for now, plus 5C equals 33, and I guess we can leave those decimals, or if you don't want to mess around with them, you don't have to. You can just write it as 33. Okay, and then now for A, we are going to make the substitution with 1850 minus 3C. So what happens is, the goal with substitution is, at this point, this new equation that we have created, you should only have 1 variable. So as you can see, the only variable we have in here is now this variable C. So that's kind of the idea of using substitution, so that you can have the entire equation in only 1 variable. And then of course we are trying to solve for C. So we'll take this 2 on the outside, distribute that inside the parentheses. So you're basically taking 2 times 1850, which comes out to be 37, minus 2 times 3c, of course, will become 6c, plus 5c equals 33. Of course, go ahead and combine your common terms. We can go ahead and subtract this 37, move it to the other side. Okay, so let me see, that was Maria. Okay, so move that 37 to the other side. And let's see, negative 6c plus 5c, of course, will end up giving us just a negative 1c or negative c. And 33 minus 37 will, of course, end up giving us negative 4, right? So just move that negative to the other side. You can multiply or divide by negative 1. And remember, these are ticket prices we're talking about, right? So you should get a positive answer. So this is actually telling you that the prices for Charles tickets are $4. Okay, so once you get the value for C or one of those variables, you can basically take it back into either equation 1 or equation 2 and calculate what the ticket prices for the adults will be. So in this case, I guess we can use the second equation, A plus 3C equals 1850. So let's go back and find that A. And what do you think that adult ticket price comes out to be? So once we plug in as C equals 4, what do we get for A? Yeah, very nice, Julian. You will get $6.50 for the adult ticket prices. And, just as a quick check to make sure that, we did our math correctly, you can go back to your original equations and, plug in $6.50 for the adult ticket prices and $4 for the children tickets. So if we take that first equation and you just do 2 times 650 plus 5 times 4, you want to make sure that is going to end up giving you that total of $33. And if you just do a quick check, 650 multiplied by 2, of course, will end up giving us $13. And then plus 5 times 4 will give you 20. So when you add that 20, with the 13, you will get 33. So you get a true statement. You can do, again, a quick check with the second equation also. So that would be 650 plus 3 times 4. And of course, you will see this will add up to 1850 again. So just do a quick check, to make sure that the calculation you have done is in fact going to satisfy your original equation. So just a quick check, and you can do this on your calculator. You don't have to write it out, but it's always a good practice to know that the numbers you came up with will in fact satisfy your original equations. So this is your substitution method. Now let's look at our second example over here. And this one is talking about a rancher has some normal cows and horses. One day he observed that his animals have a total of 96 legs and 24 tails. So how many of each type does he have? Now, when they're saying normal horses and cows, they basically mean that, they have all the limbs, they have, you know, their tail. So none of them would be, you know, missing a leg or something like that. That's just what they mean by that normal. So in this case, again, you can say C could represent, you know, the number of cows. H could represent the number of horses, or again, you can use X and Y. So the question here they're asking is basically how many of each type of these animals do they have? So we know a normal horse or a normal cow will have 4 legs and 1 tail. So that's kind of the information we want to use when they're telling us that he observed that the animals have a total of 96 legs and 24 tails. So that would be, you know, 4 legs for the cows, 4 legs for the horses. So that should add up to 96 legs. The cow has 1 tail, horse obviously also has 1 tail, so that should add up to a total of 24. So the idea here is, okay, so we've taken those legs and tail into consideration, which is how we actually come up with our system of equations. So this can be equation 1, and this can be equation 2. So since we used substitution in the last example, we'll go ahead and use the addition method here. So for the addition method, the idea is pick one of your variables, either C or H, and you want to try and eliminate it. Remember, it's called the addition or the elimination method. And so let's say we want to get rid of the variable C. So if you want to get rid of the variable C, you will need to take your equation 2 and multiply it by -4, because since my equation 1 has a positive 4C, if I want to eliminate C from the second equation, using the second equation, I need to have a coefficient of -4 on my C so that I can cancel it out. So you're going to take the second equation, multiply the whole thing by -4. So, you know, of course, that will end up giving us the first equation will keep as it is. So 4C plus 4H equals 96. Now we are multiplying, of course, -4C with the C. -4 times H will, of course, again give us -4H. And -4 times 24 will also give us -96. So you're basically taking each term of your equation and you're making sure you're multiplying by that -4. So as you will notice in this case, when you try, after you have, you know, finished the multiplication, when you add these equations, what are you going to notice about your terms here? What happens when you add these?
They cancel out.
Yeah, very nice. They are all going to cancel out. And, you know, we kind of had an idea that this should probably happen because, you know, your horses and cows, they all have 4 legs, they all have 1 tail. So there's really no way of distinguishing if, you know, they're only giving us this information. So here you can see positive 4C, -4C cancels out. Positive 4H, -4H cancel out, which means we get 0 on the left-hand side. Positive 96, -96 cancels out. So you're actually ending up with a true statement over here. And remember, this only happens, you only get a true statement when you have infinitely many solutions. So in this case, of course, we cannot say infinite since we know there are only a total of 24 animals at this farm. So the idea is you could literally have 1 cow and the remaining 23 could be horses or, you know, any of those combinations. So instead of infinitely, we'll just say there are lots of solutions. And basically, remember, this is a dependent system when you end up getting, you know, infinitely many solutions, basically. If you had gotten a false statement, which means 0 on one side and maybe like a number 6 on the other side, if the 2 sides did not match and you got a false statement, that's the scenario where you have no solution. And remember, in terms of lines, that basically means there are 2 parallel lines. Now, if this example was going to work out, then just like you saw in the previous example over here, the C, stayed and gave us an answer. So in this case, let's say we were trying to get rid of our variable C, then H should have stayed behind if we were going to come up with a single answer. So just a different way of, showing you how that infinitely many solutions type of example can end up looking like here with this ranger example. Okay, so you will have lots of solutions. We really cannot say based on the information they have given us how many of each type of these animals the ranger will have. So keep in mind when we are working through these system of equation type of examples over here, we don't really prefer the graphing method, especially if the part where the two lines actually intersect, but they don't intersect at integers. If your answers are going to be like fractions or decimals, then the graphing method really does not help us come up with the exact answer in this case. So that's why we want to stick with the substitution or the addition method. So do you guys have any questions with those two methods before we move forward to our 5.2 section? None at this point. Alrighty. Okay, let's go ahead and take a look at our 5.2 then over here. Okay, so this one is actually where we're getting into, as you can see, linear equations that will have three variables. So we're actually talking about a three-dimension coordinate plane over here. So if you take a look at this handout, okay, so we are talking about linear equations with three variables, and you can think of those variables being as your x, y, and z. So your equation will actually have this form: ax plus by plus cz equals d, where of course your coefficients a, b, c, and the constant term d are all going to be real numbers. And for our coefficients a, b, and c, we don't want all of them to equal to 0. So you can kind of think of an example like this over here: x plus y plus 2z equals 9. Now, the only reason these equations are called linear equations is mainly because they look like a linear equation in two variables, which looks like the form ax plus by equals c. So since the form is similar to our linear equation in two variables, we call these also as linear equations in three variables, but your graph is not going to be a straight line for these equations. So just kind of keep that in mind. Even though we give it the title of a linear equation, the graphs are not going to be straight lines. So they're talking about when you're looking at a solution for these equations, you know how we have an ordered pair for linear equations in two variables? In this case, we would have an ordered triple, because obviously we are looking for a value for all three of our variables, x, y, and z over here. So this equation that we are looking at, x plus 2y plus 2z equals 9, their solutions can be ordered triples like 1, 2, 3, 4, 5, 0, 3, 4, 1. These would all satisfy this equation, x plus y plus 2z equals 9. And you can just plug in those numbers for x, y, and z and make sure that you're getting a true statement. So again, it's called an ordered triple because we would put these in alphabetical order. So as you can see, the first variable, the first solution would be for the x variable, the second one for y, and the third one for z. So when you look at the ordered triple, 3, 4, 1, that means 3 is for x, 4 equals y, and of course 1 equals z. So just like with our linear equations in two variables, you can have infinitely many solutions. You can also have infinitely many solutions for these linear equations in three variables also. And when you actually think about the graph of these equations here in the three variable, you're actually looking at, and you can see this coordinate system over here. You will see how you have a three-dimensional, because you have three different axes in this coordinate system. So we've got our X and Y as your, I'm trying to see how I want to say this, because let me see, your X and Y are actually going to be the two horizontal axes. So what's going to happen is your X and Y are literally going to be horizontally placed at a 90-degree angle. So let me see if I can grab some pencils and pens over here. Okay. So if we think of our X and Y plane literally horizontally being set at a 90-degree angle to each other, your Z axis is actually going to be the vertical axis. So, you know, normally we think of X as being the horizontal axis and Y as being the vertical axis. Now we're laying them down flat as our X and Y axes, and then your Z is actually going to be the vertical axis. So this is kind of how you want to think about this three-dimensional coordinate plane. So what happens is when you try to graph these, and let me go back to our handout over here. So when you try and graph these three-dimensional equations, or the equations in three variables, your graph is actually going to be a plane. So if you think about it, it's basically like a piece of paper that will keep growing in all directions. So it basically keeps growing with no edges. It's just this infinite sheet of paper that's going to keep growing. So you're actually getting a plane as your graph, and you can see that right over here. The graph of a linear equation, three variables is a plane. Think of that plane as an infinite sheet of paper that has no edges. And as you can imagine, you know, this is going to be something very difficult to graph, and especially if we're talking about, you know, two equations or three equations, how they could be interacting with each other. It's really hard to graph this and show it on a two-dimensional piece of paper. So we're definitely not going to be using graphing as a method to solve these types of systems. We're definitely going to be sticking with our substitution or the addition method in this case. Okay, so if you look at the coordinate plane on the left side over here, this is actually just showing you how you can plot a point 1, 2, 3 on your coordinate system. So you can see our X value is 1. So this is 1 on the X axis. So you're actually taking that 1 from here on the X axis. 2 is the Y value. So that's why you are going 2 on the Y. And so what's happening is you're actually kind of coming out of that 1 from the X axis, 2 from the Y axis. So that's where those 2 points are going to meet. And then that positive 3 is telling us how high you want to go on the Z axis. So then the 1 and the 2 from X and Y meet over here, and then they go up to a height of 3 units. And that's how you're actually graphing or plotting this point, if you will. And let me clear some of these marks out. Oops. So yeah, you are basically looking at 1 on the x-axis, 2 on the y-axis, and then you're actually counting up to 3 units. But you know, again, it's so hard to imagine this going on a 3-dimensional, because technically the 3 on the z-axis is here, but you know, again, you're trying to kind of visualize this in a 3D space, but that point actually ends up coming out over here. So it's a very interesting way that you try and graph things. So what we're actually going to be doing, and you can see this on the right-hand side graph over here, is we're actually going to be finding the vertices on each of the axes. So it's kind of like the x and y intercept if you think about a straight line. So we just want to know where this plane of x plus y plus 2 equals 9 is going to be crossing each axis at. We take those vertices from each of those axes, and then we actually just create this triangular shape, which just shows you a very small section of this endless piece of paper that you have that we're trying to graph. And you know, that's the best thing we can do when you're trying to graph these. So again, just kind of remember that this is an endless piece of paper that you're thinking of as your graph for these linear equations in three variables. So they're talking about one way to draw a representation of a plane in a three-dimensional coordinate system is to draw a triangle whose vertices are the points of intersection where the plane is basically crossing the axis at. Okay, Audrey, not a problem. Thank you. All right, guys, so let's take a look at our example over here. We have x plus 2y plus z equals 6, and they're asking us to try and graph this in a three-dimensional coordinate system. So this graph on the right-hand side is kind of what we are trying to achieve in our example over here. You know what, let's do this over here. Okay, so we are given the equation x plus 2y plus z equals 6. So the first thing, like I said, is we are going to try and get those vertices where the plane will be crossing each of those axes at. So how about we start by finding for the x-axis, which means we can take our y value, set it to 0, take our z value and set it equal to 2. So this way we can find what the value for the x is. So x plus 2 times y, which would be 0, plus z, which is also 0, equals 6. So in this case, of course, you can see this guy is a 0, this guy is a 0, and we end up getting x equals 6. So our vertex here would be 6 for the x value, 0 for the y, 0 for the z. Now let's go ahead and find our y value. So we can make x 0, z 0, and then we want to find out what the y value is. So again, in our equation, x will be 0. We have 2 times y plus z will be 0 equals 6. So can you tell me what this ordered triple will end up looking like with the y value? Okay, so when you write it as an ordered triple, yeah, very nice, Meredith. Yeah, because these guys again are 0, so they are gone. You're basically left behind with 2y equals 6. Divide both sides by 2, and then of course 6 divided by 2 will give you 3. So your ordered triple is where x is 0, y is 3, and z is 0. So we've got our x and our y vertices. Now let's calculate the z, which means in this case we would be making our x value 0, y value 0, and then we're finding the z. And remember, your equation is x plus 2y plus z equals 6. So that's x is 0, 2 times y is 0, plus z equals 6. So what is this ordered triple looking like? Yeah, very nice. Because again, x and y were 0, so you end up getting 6 as the value for z. And so, of course, that would then end up giving us, there we go, 0, 0, 6. All right, very good job, guys. Okay, so now it comes down to graphing these. I actually don't like the way they have that set up, so I'm going to do this freehand and hopefully not make a big mess out of it. So in this case, remember Z is going to be our vertical axis. So the horizontal one is going to be our X. At a 90-degree angle from it, we would have Y, but again, we're trying to draw this three-dimensional graph into a two-dimensional space. So I'm actually just going to do this at an angle. This will be our Y axis, and then the vertical one is going to be our Z axis. You know what, let me try doing the vertical one first. So this would be the Z axis, and then at the angle would be our Y axis. And the way we are going to label these, we need to go out 6 units. So 1, 2, 3, 4, 5, 6. Positive 6, of course, on the left-hand side, we would have the negative X values. Okay, with the Y axes, your positive values are actually going to be towards the side facing us. So this would actually be our positive. So positive 1, 2, 3, 4, 5, 6. And this would be the negative side. 1, 2, 3, 4, 5, 6. So this is our negative side on the Y-axis. So kind of think of the side that is facing away from you would be the negative side. With the Z, positive would be on the upper half. So that would be 1, 2, 3, 4, 5, 6. That's positive 6. And 1, 2, 3, 4, 5. And negative 6 down here. Okay. So our vertices, let's start with the X, was at 6, 0, 0. So of course that would be the point right over here. The vertices for the Y-axis was at 0, 3, 0. So it's actually going to be right over here. And then for the Z was also at 0, 0, 6. So that would be the vertices right over here. So using these 3 points, you are going to be kind of creating that triangular part of our plane to just connect all 3 of those edges. Okay. And then, you know, it's always a good idea to kind of see if you can find a test point and make sure it's going to fall on this little plane of a triangle that we have. So you can do a quick calculation for your checkpoint or test point, whatever you want to call it. And in this case, you can actually just pick a couple numbers for your X, Y, and Z values, and, you know, maybe pick 2 values, one for X, and in this case, I'm actually going to go ahead and pick a value for Z and then work backwards to find what the Y value is. So we can say, okay, let X equals 1 and Z equals 1, and then we'll find Y. So remember, our equation is X plus 2Y plus Z equals 6. So that would be 1 for X, 1 for Z. And we're working backwards to find what the Y value could be. So of course, this comes out to be 2Y plus 2. Move that 2 to the other side. And we of course end up getting 2Y equals 4. And you know, this will give us Y equals 2. So our ordered triple in this case would then come out to be 1, 2, and 1. So we can use that to kind of plot it and see, is it going to fall on this little triangular region that we just graphed. So 1, 2, 1, that's going to be 1 on the X-axis, 2 on the Y-axis, and then 1 on the Z. And again, you're kind of going out from 1 over here, 2 over here, and then going to a height of 1. So somewhere over there, and you can see it's sort of falling onto our plane. So that's just a good way to know, you know, of course, we are kind of staying on that same plane. But this is the best we can do as far as graphing these linear equations in 3 variable goes, because remember, again, these are endless. sheets of paper, because this is a plane which just keeps growing in all directions. So you can kind of think of, you know, the wall that might be in front of you, and just think about how that wall is just growing vertically and horizontally in all directions. And that's what this sheet of paper or this plane is going to end up looking like. And this was just one equation. Now imagine if this was a system that had two equations or three equations. How would we exactly graph that so we can try and see what kind of interaction these planes are doing with each other? And that's the part that, you know, we really have the most difficulty with. So we are going to, again, as I mentioned, try and solve this only with the substitution and the addition method. So we'll get into that, but let's just go over this little paragraph over here. So the triangle, remember, is just to give us an idea of where they are crossing those three axes at, but you know, obviously we're not seeing the entire graph over here. They're saying it's fairly easy to draw a triangle through the intercepts that represent a plane, but you know, when it comes down to drawing 2 or 3 different planes, it's definitely going to be very hard to see how they are going to intersect with each other. They're saying often we will refer to the graphs of the equations, but we will not attempt to solve these systems with 3 variables by graphing. You can use the substitution addition method, or if it helps, you can definitely do a combination of both of them. Okay, so let's start out with our first type of example over here. We're talking about independent systems. So the same terminology as you saw in section 5.1, the independent basically means you are going to have a single solution. So they're saying you can have one solution, you can have infinitely many solutions, or your system can have 0 solutions. When we're talking about an independent system, we are talking about a single solution. So you would have a single ordered triple. So if you can see in this image over here, you have 3 different planes. You have one which is kind of this light, I don't know if it's a green color or whatever, but this is plane 1. In this almost yellowish mustardy color, you have plane 2. And then in this bluish purplish, you have plane 3. So those 3 planes are all intersecting at one single solution. So with each other, you know, they could be intersecting, if you just look at 2 of them, at maybe more than a point, but all 3 of them have only that one single point in common. So that's what makes this an independent system, because you would have a single solution. So the steps for solving any system of equations with 3 variables is actually going to be of reducing it down into a system with 2 equations and 2 variables. So what we're actually doing is taking a system like you're seeing here in example 2 and converting it into a system like what we talked about here in section 5.1. So you're breaking it down into a system which has only 2 equations with 2 variables. So that's going to be our first step as we start looking at how to solve these system of equations. Then they are saying look for the easiest variable to eliminate. You can use the addition or substitution method. So, you know, whichever one seems to make more sense. They are saying you can also eliminate the chosen variable from the first and second, the second and third, or the first and third equation. So we'll kind of talk about those pairings here. Solve the system of your equations, you know, once you have it reduced down to 2 equations and 2 variables. And then of course you're going back to what we did in section 5.1 for solving them, but make sure you are coming back and checking those 3 x, y, and z values in your original system to make sure we did not make a mistake, you know, we didn't kind of mess up and get a wrong answer in there. So let's take a look at how we can go about solving something like this over here. Okay, so we are given x plus y plus z equals 9, x minus y plus 2z equals 1. x plus y minus z equals 5. Okay, so this will be equation 1, equation 2, and this would be equation 3. Okay, so let's take a look at how we can go about solving this. So remember, our first step is to rewrite this as a system that has two equations with two variables. So the first thing you want to do is pick whichever one you think is the easiest variable to eliminate. And in this case, what I normally do is I look for an equation, a variable that has coefficient of 1 or -1. And yeah, you want to look for that positive and negative signs. So when I look at these three equations over here, z is a good enough candidate, but my second equation has a 2z, that 2 in front of the z, so I probably would not be selecting z in this case. Instead, you can see y. Two of my equations have plus y, and the middle one has minus y. So you can see if we actually use the addition method and add equation 1 and 2 or add equation 2 and 3, those y's would end up canceling each other out. So y is actually going to be a good variable to eliminate over here. So let's start with that one. Okay, so we are actually going to eliminate y. Okay, so we are going to start by taking our first and second equation. So let's see, x plus y plus z equals 9, x minus y plus 2z equals 1. So we're taking our equations 1 and 2, and we're simply adding them. So we're using the addition method over here, and you will see when we add them, that positive y and negative y will cancel out, and you will end up getting x plus x, which is 2x, plus z, which is 1z plus 2z. Of course, 1 plus 2 will give us 3z. And then on the other side, 9 plus 1 will give us 10. So you can now see this is an equation with only two variables. So this is kind of how we are actually reducing our system down. So let's call this equation 4. Now we need one more equation to make our system, with two equations and two variables. So since we added 1 and 2, for the next equation, we will go ahead and add 2 and 3. So just, obviously we don't want to add 1 and 2 one more time because we'll still get the same result. So this time we will go ahead and add 2 and 3. So that's going to be, let's see, x minus y plus 2z equals 1, which is equation 2. Our equation 3 is x plus y plus z equals 5. Okay, so we're adding equations 2 and 3. And again, obviously our goal was to eliminate y, and you will see again that negative y and positive y cancel each other out. So when you add these two equations, we end up getting x plus x, which is 2x, 2z plus 1z, of course, again adds up to 3z, and 5 plus 1 will end up giving us 6, and this will be equation 5. Did I write that incorrectly? Yeah, that should be a negative z. I don't know why I made that positive. Okay, so actually this has to be negative, which means this answer will change, which should actually only be a negative z. I'm not sure why I made that positive. Okay, there you go, because that would not get us the correct answer if I made that mistake. All right, so we've added equations 1 and 2. We've added equations 2 and 3, which gave us these two new equations. So now we have reduced our system down to 2x plus 3z equals 10. This is our equation 4. And then we have 2x minus z equals 6. And this is equation 5. So basically, we now have our system of two equations in two variables, and then using the techniques you saw in section 5.1, you can go about solving these. So if you look at the equations 4 and 5, you can see both of them have a positive 2x and positive 2x, for those x variables. So if we can make one of those into a negative 2x, we can again use the addition method to go ahead and cancel out our x variable in this case. So what we will actually do is take our either the first or the second equation and just multiply it by -1. So in this case, then our first equation will stay the same, 2x plus 3z equals 10. We're keeping him the same. Our second equation, of course, remember to distribute that -1 all the way through. So that will end up giving us -2x, negative and negative will make that a positive z, and then 6 will become negative. So now we can go ahead and add these two together, and this is what we were hoping, that our x would eliminate or cancel out. So positive 2x, negative 2x cancels out. And of course the z will stay behind. So we've got 3 plus 1, which will be 4z, equals 10 minus 6 is 4. And you can see, of course, our z value now comes out to be 1. Okay, so you've got an answer for z, and this is a good sign because this definitely tells us that we will be able to find that one single solution where all three of these planes are intersecting with each other. So now that you have found z, you want to go back to either equation 4 or 5. We're not quite ready to go back to the originals because, to be able to find x and y, we don't have either of those numbers just yet. So once you find this answer for z, go back to your equation 4 or 5 and then plug in that number and work backwards to find the x. So we can use our second equation, 2x minus z equals 6, to help us find the x value. So let's start by finding x. That's 2x minus z. What is that? Okay, I made a mistake here again, didn't I? Because apparently I am just not using my brains here, guys, today, because this is positive 2 and minus z, which should have been plus z. Yep, which would then make this, okay, I kept a plus over there, so this was fine. I am getting z equals 1. Okay. Hold on, I'm going to go ahead and actually erase myself because this isn't correct. Okay. I just realized looking at my handout that my answer is not coming out to be correct over here. So when we added equations 2 and 3, this should have actually been 2x plus z equals 6, which is what I have here. Which would have then given us keeping our first equation the same. 2x plus 3z equals 10. We had minus 2x minus z minus 6. So when we added these, our 2x canceled out. Oh, there we go. This should have been 3z minus z, which would actually give us 2z. We would have had 4 on this. There we go. And then we would divide by 2, which would then end up giving us z equals 2. There we go. Okay. Sorry about that. I don't know why I did that. I keep changing signs on myself here. So you should actually have z equals 2, and then when we go back to find x, okay, and then we'll use equation 5, which is 2x plus z equals 6. And our z value is 2. That should be positive. Okay, working backwards, move that 2 to the other side. And that will give us 2x equals 4, divide by 2. And looks like our x value is also coming out to be 2. Okay, so now we have our z value, we have our x value. So of course you can see, since we have both the x and the z, we can no longer use 4 and 5. So now once you have 2 of those answers, you can go back to the original 3 equations and try to find that last missing variable, which in this case would be y. So you can use any of these equations. I think I'm going to use equation 1 over here, x plus y plus z equals 9, to help us find the y variable. So x plus y plus z equals 9. Both our x and z values are 2, so that's going to be 2 plus y plus 2 equals 9. And of course, you can see that comes out to be y equals positive 5. Okay, so our ordered triple that we are looking at is going to be 2, 5, and 2. And so we want to verify that it's going to work for all of these original equations. So do a quick check over here to make sure it's going to work. So for the first equation, we've got 2 plus 5 plus 2. And of course, you can see this will end up giving us 9 equals 9. So we know it's going to work. For the second equation, you will have 2 minus 5 plus 2 times 2 equals 1. And so you can see 2 minus 5 would be negative 3. Negative 3 plus 4 would be 1. So you will end up getting 1 equals 1 for the second equation. And then for the third one, we have 2 plus 5 minus 2. So of course, that positive 2 and negative 2, you can kind of think of them canceling each other out, and you would end up getting 5 equals 5. So it checks out for all 3 of them. So always make sure you are checking in the final, your final ordered triple in the original 3 equations. And so this here is going to be our solution set. And remember, this is an independent system when you have one single solution for your system of equations. So question on this one, aside from that, blunder I made with z equals 2. Any questions that come to mind, guys? No? Okay, so remember the key thing here is to start out by reducing this from a system that has 3 equations with 3 variables and breaking it down into this system where it's a system of 2 equations with 2 variables. So then you can go ahead and find these 2 variables first, which was the x and the z. Once you have those 2 answers, then you can go back to any of your 3 original equations to find that last missing variable, which would be y in our example here. And that's how you can come up with your ordered triple. Alrighty, if you guys don't have any questions, we'll move on to our next type of system, which is with infinite solution sets. So they are saying you can have 2 planes in a 3-dimensional space. So just think about two pieces of paper. They can either be parallel to each other. So of course, if they are parallel to each other, they are not going to touch, which means you would have nothing as a solution set. Or think about two planes of paper which would intersect each other. So if you think about two pieces of paper intersecting each other, they are actually going to be intersecting at a straight line. And you can look at this graphic over here. So on the left-hand side, we've got two pieces of paper. And this one they're placing kind of perpendicular to each other, but they don't have to be. But the idea is when these two pieces of paper are touching each other, you will see they are actually forming this little line of intersection over here. And since these are endless pieces of paper, that line where the two pieces of paper are intersecting is also going to be a long infinite line, which means it's going to keep growing in both directions. So that's why you are actually going to end up getting infinite solutions, because all of those points on those two planes are actually going to be your ordered triples. So you will have infinite of these. If you look at the graph on the right hand side, this is three different planes over here. And you can see again how they are also intersecting at a single individual line. So that also tells us we will have infinite number of solutions. So you can have two planes intersecting each other, or you can have three planes intersecting each other. So all of those will end up giving us an infinite number of solutions. So keep in mind, if the two planes are intersecting, they intersect along a line, and that means we will have infinitely many points to satisfy our equation. If the planes are parallel, then of course you would have no common point, which means we would have no solution to our system over here. So we're starting out with two planes in a three-dimensional space. So let's go ahead and take a look at what kind of solution set we get here for number 3. Okay, so we are given x plus y plus z equals 2, and then x minus 2y minus z equals 4. Okay, so these are our two equations over here. So again, you want to pick one variable that you can easily eliminate. So when I look at these two equations, that z is looking really good because we've got a positive and a negative z. So we can go ahead and start by eliminating z first. So take our equations, x plus y plus z equals 2, x minus 2y minus z equals 4. Add these two equations together. So plus z minus z cancel each other out. And when we end up adding this, we get 2x plus y minus 2y would be minus y equals 6. And this can be our equation 3. But here's the problem that we're going to run into. You don't have a third equation over here to create a system of equation with two variables. So whenever you see an equation or a system like this where you only have two equations with three variables, you have to imagine you're either going to have, like we said, the two planes are parallel to each other, which means we will not be able to find an answer for x or y. And if they are infinitely many solutions where the two planes are intersecting at a line, then we would actually see something very interesting, which is actually looks like kind of what's going to happen over here. So I am actually going to take this equation and get y by itself, move my 2x to the other side. So we can start by taking this 2x, moving it to the other side, and we are left behind with negative y equals minus 2x plus 6. Get rid of that negative, so divide everything by negative 1. And we will end up getting y equals, that will become a positive 2x, that will become a minus 6. So we're actually going to go ahead and rewrite our equation 3 over here. Now what's going to happen actually is basically if you go ahead and put this y equals 2x minus 6 in your original equations, let's see what we're going to come up with. So we're going to take that first one, which is, I need my piece of paper over here, just a second. Okay. So our first equation is x plus y plus z equals 2. So we're going to take our y and we're going to make the substitution with this 2x minus 6. So that will end up giving us that x at the front will stay as it is. Instead of y, we are going to write 2x minus 6 plus z equals 2. And this is, of course, our first equation. So when you clean this up, you would end up getting x plus 2x minus 6 plus z equals 2. If we combine our common terms, we end up getting 3x minus 6 plus z equals 2. We'll go ahead and add that 6, move it to the other side, and I'm actually also going to take my 3x and move it to the other side. So you're basically getting that variable z by itself, and you end up getting z equals, what would this be? 8 minus 3x, okay? Let's call this equation 4. So we've got equation 3 as y equals 2x minus 6. We've got equation 4 as z equals 8 minus 3x. So you will see again, we have rewritten both y and z in terms of x over here. Now, if you actually try and plug these x and y values into your second equation, equation 2 over here, let's see what that ends up looking like. So you've got x minus 2y minus z. And this equals 4. This is our second equation that we had. So x will stay as it is. We are going to substitute y by using, again, this 2x minus 6 here from equation 3. We are also going to make our substitution for z by using this 8 minus 3x. Okay, so let's clean this up and see what happens. You'll need to take this negative 2, distribute it inside the parentheses. We'll need to take this negative sign, distribute it inside the parentheses, which will end up giving us x, what's that, minus 4x. Negative and negative would be positive 12 minus 8. Hold on, that should be positive 3x equals 4. So when we clean this equation up, what are we going to end up getting? Because if we combine all our x terms together, I've got positive x, negative 4x, which will become negative 3x, negative 3x, positive 3x. So they should actually all end up canceling each other out. With the 12 minus 8, you will see we end up getting 4. So you actually end up getting 4 equals 4, which is again a true statement. So what's happening in this case is if you had ended up with a false statement here, we would know these two planes are parallel, so they have no solution. When you end up getting a true statement, that's actually telling us these two equations are basically intersecting at that one single line. So this equation actually set up will end up looking like something on the left-hand side where the two planes intersect at a straight line. And so that's why you are actually going to have infinitely many solutions. But you can see the process of solving this is just a little bit different than what we did in the previous example. We started out by eliminating our z variable. So we got rid of z. You ended up with 2x minus y equals 6. And we ended up getting just y equals 2x minus 6 by rearranging that equation 3. Then we took the same first equation from our system over here, and we plugged in for the y value, 2x minus 6. So when you simplify that equation, we were able to rewrite it as z equals 8 minus 3x. So what we have actually done is taken our y value and written it down in the terms of x. We have taken our z value, and same thing, we have rewritten it in terms of x also. So both y and z are actually written in terms of x. And then when we took those two definitions and put it into our second equation from our system, you can see we ended up getting a true statement. So when you get a true statement, that tells you you have infinitely many solutions. So this would be infinitely many solutions. Now, the way you actually write these answers, the solution set is going to be a little bit different. If they want us to write the answer in terms of x, then you would actually write it as, and let me make sure I'm writing this correctly. Okay. So the way we are going to write these is going to be kind of using our set builder notation again. So we take our ordered triple of x, y, and z, and we're saying this can come from y equals, and remember we had equation 3 as 2x minus 6, y equals 2x minus 6, and z equals, I had written it as 8 minus 3x. I'm just going to rewrite it as minus 3x plus 8. So what I'm actually doing is just using this z defined in terms of x, y defined in terms of x, and using set builder notation to write it. This is one way of writing our solution set, but I think actually MyMathLab wants it in a different way. So I think MyMathLab may actually want you to write this like, okay, our first value is x, and x obviously is going to stay as it is. Instead of y, again, you're going to use this definition of y equals 2x minus 6. So this guy would be 2x minus 6. Z, again, we would write it as z equals negative 3x plus 8. So you would have negative 3x plus 8. So instead of writing x, y, and z, you're actually writing x as the variable itself, but then y in terms of x, z in terms of x, and then you would say x can be any real number. So this is actually how MyMathLab will want you to write it. But there's another twist to this. This can all be in terms of x, which is what we have right now, but they may want you to write it all in terms of y. So instead of having x, in terms of x, they may want you to, oh, come on, buddy. They may want you to write this in terms of y, where you can say y is any real number. So that means we would then have to rewrite our x variable in terms of y. We would leave the y as it is, and then z also in terms of y. And I'll show you how to rewrite that. Or they could want your answers to be in terms of z. So they may want you to leave z as it is and then say z is any real number. So it actually can keep changing depending on how MyMathLab is asking you to rewrite this. So if it wants you in terms of x, that's exactly what we had done. So we already have the definition for y and z in terms of x. But if they wanted us to write in terms of y, that what you're actually going to do is take this equation that we had here in equation 3 and get x by itself instead of getting y by itself. So if you had to rewrite this in terms of y, then you would actually have, let's see, our original equation was 2x minus y equals 6. We're going to start by moving that y to the other side. Then you would have 2x equals y plus 6, divide everything by 2. So we would end up getting x equals 1/2 y plus 3. So x equals 1/2 y plus 3. So that's what you would have over here then, as x equals 1/2 y plus 3. And then we would have to actually go back and rewrite z also in terms of y. So this is where you would then take your z equals 8 minus 3x, but instead of x, you're going to substitute it with this 1/2 y plus 3. So then instead of x, we would have 1/2 y plus 3. We would need to clean this up. What would that be? Minus 9. So this would then come out to be negative 3/2 y, and looks like plus 1. No, that's a minus 1. So now your z variable is defined in terms of y as minus 3/2 y minus 1. So now this guy here would be minus 3/2 y minus 1. So that's kind of how this whole rearranging process works. So you really kind of have to see in your solution options what exactly is MyMathLab giving you. Is it asking you to write it in terms of x, in terms of y, or in terms of z? Now if they're asking you to write this in terms of z, then we actually go back over here to equation 4, and instead of getting z by itself, we would actually try and get x by itself, which means you would actually have to do this as let's see, what did we have? Z equals 8 minus 3x. So now we're trying to get x by itself. So of course we would start by moving the 8 to the other side. You would have minus 3x left behind, and then obviously divide everything by minus 3. So then you would end up getting x by itself on the right hand side. We would have negative 1/3 z, and that would become positive 8/3. So now you have written z, you've written x in terms of z. So when you put this in your answer solution here, instead of x, we would now have negative 1/3 z plus 8/3. Right? So now you take this value of x, and you know that's kind of the part that you really have to be careful about, because now we also need to rewrite y in terms of z. So you are going to take this definition of x, which is negative 1/3 z plus 8/3, and you're going to go back up here to the y value and substitute the x in this case and try and come up with your answer. So now you have y equals 2x minus 6, but replace that x with the negative 1/3 z plus 8/3. And now you want to write y in terms of z. So there's a lot of, you can see back and forth going on in this case. And so this would now become negative 2/3 z. And what would that be? 16/3. And then minus 6, you're going to have to clean that up, which will end up becoming negative 2/3 z minus 2/3. Because 6 times 3 would be 18. So yeah, minus 2/3. Now this guy will be minus 2/3 z minus 2/3. Okay. So y in terms of z is minus 2/3 z minus 2/3. So you can see when you are writing these guys in terms of x, if x is the variable they want, then x will stay as it is. So this guy will be the variable x itself. But now y is in terms of x, z is in terms of x. If they wanted us to write this in terms of y, then the middle variable y will stay as it is, but then now you have x in terms of y, z in terms of y. And same way, if they want us to write z as our final variable, then the variable c in the ordered triple will stay as it is, but then x is now in terms of z, y is now in terms of z. So be very careful when you are looking through these examples. And let me actually just quickly show you what I'm talking about here in your MyMathLab. Okay. This would be in section 5.2. Okay, so if you look at this example over here, now obviously we don't know what kind of solution set they have, but if option B was going to be an answer, you can see how they want this as in terms of Z. So if you were looking at the type of example we just did, and you had to rewrite your X and Y are basically going to have to be in terms of Z now. So you kind of have to pay attention to that. Let's see. Looks like number 6 is also asking you to write this in terms of Z if, you know, that ends up being your type of answer. And looks like this guy is also in terms of Z over here for number 7. And let's see what number 8 is showing. So it looks like actually all the examples are asking to write this in terms of Z if, you know, the infinitely many solutions is what you end up with. Now, if you get one single solution, then of course you don't have to worry about it. If you have an empty set, you don't have to worry about it. But if it's going to be infinitely many solutions, then just make sure you are writing these in the variable that they are requesting you to write this in, which would actually then end up being this last form that we were looking at if you end up with infinitely many solutions. Now on piece of paper, you know, this would have been acceptable, but as you can see, MyMathLab is not asking you to write it in this form. So for MyMathLab, you're not really doing it in this form, because that would definitely be a lot more easier to work with, but they are asking you to write it as one of these. Okay, so just kind of keep that in mind when you are looking at these types of examples that have infinitely many solutions. Okay, so this was an example for a system of equation that has only 2 equations and 3 variables. Now your next example is a system of equations with 3 equations and 3 variables. But before we move on to that, do you guys have any questions on example 3 over here? Yeah, as you're working through homework and, you know, something comes up, please do let me know. So they are saying a line in 3-dimensional space does not have a simple equation like your line in a 2-dimensional space, y equals mx plus b kind of format. So in this example, they are saying your ordered triple was x, comma, 2x minus 6. This would be for the y value. Negative 3x plus 8 would be the z value. This is basically a point which will fall on that line of intersection, where those two planes are intersecting with each other. And this will be true, of course, for any real number x. So they are saying the points 0, negative 6, 8, 1, negative 4, 5, or the ordered triple 2, negative 2, and 2 are actually all going to be solutions to this example 3 over here, because these are the points that lie on this line of intersection. So we can't really write that with an equation of a line in this case. So that's why, we kind of end up using this set builder notation kind of concept here to help us write these ordered triples. All right, so here again, you can see this is a 3 equations with 3 variables. So let's go ahead and see how we can simplify example 4 over here. So we are given x plus y plus z equals 1. Let's call that equation 1. X minus y minus z equals 3. So that's equation 2. 3x plus y plus z equals 5, and this is equation 3. So of course, this is where you're going to want to reduce it from a system of 3 equations with 3 variables to a system of 2 equations with 2 variables. So as we look at these x, y, and z values, you can either eliminate y, because you do have a positive y and a negative y, or you can eliminate z, because we also have positive z and negative z. So this example, obviously I would not use x, because that last equation has a coefficient of 3 on the x value. So you can either use y or z. So let's go ahead and eliminate z. So just like you saw in that second example, we're going to start by adding, let's see, our equations 1 and 2. So x plus y plus z equals 1, and x minus y minus z equals 3. So what do you notice here when we add these two equations? What do we end up getting? Let's see. Lori, you've got x equals 4. Okay, yeah, because you will notice in this case, both our y variables and z variables will cancel out, right? Because you have positive y, positive z, negative z. So both of them are canceling out. Lori, you will actually not get x equals 4, because when we add x plus x, you've got 2x, right? And then on the other side, 3 plus 1 is 4. So actually you will end up with that x, you have to get rid of the 2 coefficient. So you end up getting x equals 2, right? Yeah, very good. So as you will actually notice, we were not really able to reduce this equation down to 2 variables, which is kind of what we were hoping to do in this case. Let me show you with our example 2 over here. You can see how in example 2, when we added our 1 and 2 equations, it reduced down to an equation that had 2 variables left behind. We eliminated y, but we had x and z left behind. Our goal here was to eliminate z, but obviously the y also ended up canceling out. So this again is telling you that you are not looking at a system which has only one single solution, because if this had only that one ordered triple, then the y should not have canceled out. We should have only gotten rid of the z. So this is definitely going to be a system that has infinitely many solutions or no solution, which x equals 2, of course, is telling us there's some kind of solution happening here. Alrighty, so we've added equations 1 and 2. That ended up giving us x equals 2, as our answer. So let's call this equation 3 for now. I am still going to go ahead and add my equations 2 and 3, the next two equations, and see what happens. So this is going to be, let's see, equation 2 is x minus y minus z equals 3. Equation 3 is 3x plus y plus z equals 5. So let's go ahead and add these and let's see what's happening over here. Negative y is canceling out, negative z, positive z is canceling out. So actually same thing that happened in the previous set. So when we add the remaining terms, 3x plus x will give us 4x. On the other side, 5 plus 3 gives us 8. And you will actually notice we are getting the same result over here of x equals 2. And let's call this, oh, actually, this should have been 4. Since we already have an equation 3, so that would make this guy a 5. So our equation 4 and 5 actually obviously come out to be the same number. Both of these, by adding equations 1 and 2, we also got x equals 2 by adding equations 2 and 3. We actually also ended up getting the same answer, x equals 2. So what's happening in this case is basically it's telling us, since we got the same value, this will be a dependent system. You will have infinitely many solutions. Now the question is, we want to figure out what those y and z values are going to be. Let's take a look at how we can do that. So this is a dependent system. We have infinitely many solutions. Okay, so let's start with our first equation, x plus y plus z equals 1. But now we know x is 2, so replace that x value with 2. And then you are basically either trying to get y by itself or z by itself. So start by moving that 2 to the other side. And we end up getting y plus z equals -1. So if you want to get y by itself, move the z to the other side. So you would end up getting, let's see, if we move the z to the other side, it will become -z -1. Or if you want to get z by itself, then we can move the y to the other side. So that would become -y -1. So you can write y in terms of z, or you can write z in terms of y. And if you actually try and do this on the other two equations, we'll have to kind of see, do we get same answers or different answers? So our equation 2, this was equation 1 over here. Let's see, for equation 2, what do we get? Equation 2 was x minus y minus z equals 3. So if my x is 2, let's see, move that 2 to the other side. And we end up getting -y minus z equals 1. You can actually go ahead and divide the entire equation by -1. So this would end up becoming positive y, positive z, and the 1 would end up becoming -1, which looked exactly the same as what we had from our equation 1 over here. So we would, again, if you get y by itself, we would end up getting -z -1. If we get z by itself, we would have -y -1. So this is the same answer that we got from here when we solved equation 1. Now let's see what happens if we try and solve equation 3. So equation 3 was given as 3x plus y plus z equals 5. So replace that x with 2, which would of course give us 6. Move the 6 to the other side. And again, we are getting y plus z equals -1. So same thing as the other two equations. You would end up getting y equals -z minus 1. Or if you get z by itself, that would be minus y minus 1. So you can again see, even by just plugging in that value of x equals 2 into each of our 3 individual equations, you are still getting the same values for your y and z. So this is another way that we know for certain that these 3 equations are going to be intersecting at a single line, and we will have infinitely many solutions. Now, the way you write your solution set in this case is going to be a little bit different, because we do have a static value for x. We know x is always going to be 2 because that's what we got when we solved these first two equations and the second and third equation. So our x value will always stay as as 2. But then now, do you want to write your answer in terms of y or in terms of z? So if we want to write this in terms of y, then leave the y as the y variable itself. And then z, you're going to write in terms of y. So it's actually going to be the second one. And you will have, instead of z, we will write this as minus y minus 1, where y will be any real number. Now, if they want us to write the solution set in terms of z, again, your x value is still going to stay as 2. And if they want us to write this in terms of z, that means we will be using this first definition then. So y equals -z minus 1, and then we would say z is any real number. Because, you know, again, I'm not sure in your quiz or exam how it's going to show up. Is it going to be in terms of y or in terms of z? So you should be comfortable writing it in both ways. But in this case, since your x value is a static number 2, you won't have to write this as, you know, x is any real number format. It's only going to be in terms of y or z. But again, just another example where you have 3 equations that end up giving you infinitely many solutions, and how you end up writing your solution set. So any questions here on number 4, guys? Nothing? Okay. Let's take a look at this example here. So they're saying if all your equations are equivalent, then the solution set of the system is going to be set of all points that satisfy, you know, any one of those 3 equations. So when they're actually saying you have all equations that are equivalent, if you take a look at this example over here, if I take my first equation, x plus y plus z equals 1, and if I'm actually multiplied by 2, that would give me my second equation. If I take that same first equation and multiply by 3, that would actually give me my third equation. So it's actually technically the same equation, just multiplied by 2 or 3 to give us the other 2. So in this case, actually what's going to happen is just think of them as a stack of paper, of 3 sheets of paper. So actually what's happening is all those 3 planes are just stacked on top of each other. So you can imagine this is an infinite piece of paper, which means all those points are going to be intersecting with each other. So you can just imagine they're not even meeting at a single straight line. They are basically stacked up on top of each other. So you will definitely have, again, infinitely many solutions. And in this one, they are actually using the set builder notation, where you write the first part as your ordered triple of x, y, and z, and then just use any one of those 3 equations to put at the second part. So we're just going with equation 1, x plus y plus z equals 1 in this case. So this would be your set builder notation when all 3 of your equations are equivalent to each other. All right, so we've looked at an example where the 3 planes met at one single point, which was our independent system. We've looked at 2 more examples after that, where we were looking at what happens if you have a dependent system when you get infinitely many solutions. And now we're looking at an inconsistent system over here. So again, the idea is, we are talking about these three planes intersecting with each other. And they're talking about, there's several different ways how these three planes could be positioned, as long as, we know that there is no single point which would be common to all three planes. So one of the scenarios is this graph that you're seeing over here. So we've got these three planes which are essentially making a triangle with each other. So these two planes you can see are intersecting at a straight line, but that's only those two planes. These two planes over here are also intersecting at a straight line. And then the other two planes are also intersecting at a straight line. So only those two planes are intersecting. But if you think about all three of these planes, you will notice there is no one single point which is common to all three. Kind of like what we had seen over here, where there was at least one point which was common between all of them. So that's definitely not happening over here. So in this case, since there is not even a single point in common, we would say this is an inconsistent system, and you would end up with no solution, because basically the idea is you wouldn't find an ordered triple which would satisfy all three equations. So that's kind of what you can sort of imagine when you have an inconsistent system, and what do you end up getting. So let's take a look at number 5 over here, and let's see what kind of answer we end up getting over here. So we are given x plus y plus z equals 1. Okay, x minus y minus z equals 3. And then we have 3x plus y plus z equals 7. So this can be 1, 2, and 3. So again, let's see, we have positive and negative y, positive and negative z. So again, yeah, you can eliminate y or you can eliminate z. It really doesn't matter. Let's see, how about, let's eliminate y in this case. So we can add equations 1 and 2. So in this case, the positive and negative y will cancel each other out. But like you saw in the last example, those z also ended up canceling each other out, and we end up getting 2x equals 4, which again looks like we are going to end up getting x equals 2. This guy will be equation 4. This was us adding equations 1 and 2. Now let's go ahead and add equations 2 and 3, and let's see what happens. So equation 2 is going to be x minus y minus z equals 3. Equation 3 is going to be 3x plus y plus z equals 7. So when we add these equations together, our y will definitely cancel out, but similarly you will see that z also ends up canceling out, and we end up getting, what is this, 4x equals 10. So what will our x value come out to be? So 10 over 4, what can we reduce that down to? Yeah, very good. I was kind of looking for a fraction answer, but yeah, I read it as decimal, it would be 2.5. Yeah, so you actually will notice here, and we can call this equation 5. If you were going to get a solution, you should not be getting two different x values over here. So you are ending up with x equals 2 for, when we added equations 1 and 2, and you're getting x equals 5/2 when we added equations 2 and 3. So obviously nothing like what we saw here where you ended up getting the same x value. I mean, these are obviously a system that you're solving. So if there was going to be a solution, these things should have been the same. So this actually right here where you end up getting two different x values, this tells us that this is an inconsistent system. And then of course, an inconsistent system tells us there is going to be no solution in this case. And just to kind of show you what happens with our other equation. So how about we stick with x equals 2 since that's a whole number, and we'll try and plug it into our three equations, kind of like what we did here where we plugged in 2 for our three equations, and we ended up getting the same value for y and z. Let's see what happens with an inconsistent system when we try to do that. So we'll just use x equals 2 as our main value here. And let's start with equation 1. So equation 1 is x plus y plus z equals 1. So that would be 2 plus y plus z. Move that 2 to the other side. And you get y plus z equals 1. Sorry, negative 1. Okay. If I try and do this for equation 2, what will we get? Which is x minus y minus z equals 3. So x is 2. Now let's see, move that 2 to the other side. You have negative y minus z equals positive 1, just like we did before. Let's just go ahead and divide everything by negative 1. So negative and negative will end up becoming positive. And we'll end up getting positive y, positive z equals negative 1. Okay, so actually these two are in fact the same equation. So these two came out to be the same. Let's see, do we get that on equation 3? Which I have a feeling we should not, because this is an inconsistent system, but obviously, let's take a look. So you have 3x plus y plus z equals 7 for that third one. So that would be 3 times 2 plus y plus z. So let's see, that would be 6, which is what we would subtract on both sides. And this one is actually giving us positive 1. So y plus z is positive 1, which does not match these other two that we came up with. So you can see again, like I said, since this was an inconsistent system, all three of them should definitely not have come out to be the same one. So this is also telling you again that we're going to get an inconsistent system, because think about it. I have y plus z, and y plus z on all of them. So even if you do a little substitution, if I take y plus z from one of these upper two equations, you are basically looking at negative 1 equals 1, which is of course a false statement. So again, that is telling you this is an inconsistent system. You will have no solution. And I think in my math lab, they were just asking you to select a bullet point, I think. Yeah, so if you have an empty set, you're just choosing that option C is what it looks like when you have no solution, okay? So that's kind of what you would do here for example 5. So a lot of this process is still going to be the same. If you have 3 equations with 3 variables, start by eliminating whichever variable you think is the easiest one. Start adding them. If you are getting a single solution as your answer, then you should have what we had here in example 2, where we eliminated y, but then x and z still ended up staying behind. And then we were able to get a system that had two equations with two variables like we did over here. So this one here is a new system where we have two equations in two variables. And then we were able to solve equations 4 and 5, and we eliminated x, so we kept the z value. We went back and found x, and then we went back to the original equation and found y. So this is how you know you are going to have a single answer for your system over here. So this would be our independent system. This was a little bit of a different example because we only had two variables in three equations, but again, with number 4, we had three equations again. So we started out with the same process, trying to break this down into a system that has two equations in two variables. But as we were trying to do that, you would see that both y and z canceled out, leaving us with x. When we changed the ordering of our equations, 1 and 2, 2 and 3, you can see both of these equations, 4 and 5, came out to be the same. When they come out to be the same, we know they are going to be a dependent system with infinitely many solutions. And then it was just a matter of, do you write your y and z in terms of y or the variable z? So you can see the two different options we had here. Now, if you have a system that has no solution, it's an inconsistent system, we still start out with the same process, adding equations 1 and 2, adding equations 2 and 3. But you will notice in this case, again, two variables canceled out. And the x value we ended up getting were two different numbers. So we got x equals 2 on equation 4, x equals 5/2 on equation 5. So since you're getting two different answers for x, you know it's an inconsistent system and you get no solution. Just by plugging in that value of x equals 2 into all three of our original equations, you will notice not all of them give us the same answer when you simplified them. So this was another way to just prove that we have no solution. So no solution, it's an empty set. Okay, so your process is still going to be the same, but it just comes down to what kind of answers you end up getting, and that's going to tell us if we have an independent system with one solution, a dependent system with infinitely many solutions, or you're going to have an inconsistent system with no solution. Okay. Do you have any questions at this point? No? Okay. So one of the common examples that we kind of come across with these three equations with three variables is actually working backwards to try and see if we can come up with an equation for our parabola. So they are saying just as we find the equation of a line from two given points, we can find the equation of a parabola, which would be in the form y equals ax squared plus bx plus c from three given points. Now, in this case, you know, when we're talking about points, we are talking about our x and y ordered pair because, you know, obviously a parabola is an equation with two variables. So they are saying each of the three points will actually help us come up with our linear equation in three variables. And they are saying as long as the points are not collinear, the system of three equations and three unknowns will end up giving us a unique solution. So when they are saying your 3 points are not collinear, does anybody know what that they mean by that? What do we mean by not being collinear? Because, you know, if we don't know what collinear means, it kind of defeats the purpose of what we're trying to do over here. Nobody? Yeah, very nice, Audrey. They should not be in the same line together. So as long as those points are not going to be falling in the same line, we are going to be safe over here. All right, so let's go ahead and take a look at how we can create this system of three equations with three unknowns. Okay, let me see. So our 3 points that are given to us over here, let's see. Okay, we've got -1, +1, +1, +3, and +2, +7. Now remember, these are your ordered pairs in 2 dimensions, so this would be your x and y values for each one of these. So we are looking at our parabola to be in the standard form, which is y equals ax squared plus bx plus c. So when you are actually trying to come up with these equations, what we are actually going to do is take this point, let's start with the first one, -1, +1. And in this equation for a parabola, you're actually going to replace your x and y variable. So the y variable is +1, x variable is -1. So plug that into your equation. And basically our goal here is to find those a, b, and c values so that we can put it back into our equation of a parabola. So this is actually what we are trying to find. So when we clean this up, we should end up getting 1 equals, let's see, -1 squared would become +1. So this would just be +1 times a, or positive a. B times -1 would become -b plus c. So this is actually our equation 1 for our system of, 3 equations with 3 unknowns. So can you tell me, with the ordered pair of 1 and 3, what would this equation end up looking like? What will we have? So anybody have an answer? Meredith, you've got a plus b plus c equals 3. Okay, so let's see. We've got y as 3, a x squared plus bx, where x is 1. Yeah, very nice. So you end up getting 3 equals a plus b plus c. So this will be equation 2. Okay, and then for the third one, what will we have? And our third order pair is 2 and 7. Okay, let's see, Meredith, you've got 4a plus 2b plus c equals 7. Okay. Yeah, because 2 squared would end up becoming 4. So that's 4a plus 2b plus c. And you can see this is actually how we come up with our system of equations over here. So let's put it all together. We've got a minus b plus c equals 1. This was equation 1. And I'm just kind of putting it in our standard form, variables on the left, numbers on the right. Our equation 2 was a plus b plus c equals 3. That's equation 2. And then 4a plus 2b plus c equals 7. Okay, so since this is asking us to find the equation of our parabola over here, this is actually going to be an independent system, which means we should get one order triple, so a number for a, b, and c. So this will give us one solution. So which variable would you want to eliminate here, guys? A, b, or c? Now, in this case, you know, honestly, nothing is going to be straightforward that jumps out, but your B does have the positive and negative sign, even though you do have that 2B on equation 3. But you can eliminate B because by default, you do have that negative sign built in there. If you wanted to eliminate C, you can, but obviously that means we would need to multiply one of the equations by a negative number to create that C into a negative number. Same thing for A. If you wanted to eliminate A, you know, you do have that 4A on that last equation, so you would need to make sure you take that into consideration. So in this case, I'm actually going to go with B because we do have that negative sign on that first equation for B. So you can start by eliminating B. And that means take your first two equations, add them together. And remember, this is where we are trying to break this down into a system with 3 equations and 3 variables to a system with 2 equations with 2 variables, so that positive and negative b will cancel out. Adding up, we get 2a plus 2c equals 4. So this becomes our equation 4 over here. And again, you can see both our a and c variables will stay. In that same way, we can go ahead and let's see, add. Since my negative is on equation 1, I am actually now going to add equations 1 and 3. I've already added equations 1 and 2. So now I'm going to add equations 1 and 3. So that would again give us, let's see, a minus b plus c equals 1. And 4a plus 2b plus c equals 7. And obviously, I will not be able to add them straight away because we do want to eliminate B. So what do you think we need to do over here to eliminate B? Because I've got negative B and positive 2B as my coefficients. So what would you do to eliminate B over here, guys? Yeah, you want to multiply equation 1 by positive 2 so that you can make this into a negative 2b over here. So that would end up giving us 2a minus 2b plus 2c equals 2. Keep that third equation the same. So 4a plus 2b plus c equals 7. And then when you add these guys together, you will see that b term will cancel out, leaving us behind. It looks like with 6a plus 3c equals 9. And you can call this as your equation 5. So now we have our system with equation 4 and 5. 2a plus 2c equals 4. And then, of course, we've got 6a plus 3c equals 9. So now that we have our system, we can go ahead and, you know, solve this system. So we'll pick up from here tomorrow, guys. If you want to work on this and see what kind of answer you get, you're welcome to work on it, but I'll show you the second half of this problem tomorrow. Okay. All right, guys. So I just wanted to give you a quick heads up. We only have one section more in chapter 5. So you literally have 5.2 and 5.3. So again, this week you are looking at finishing chapter 5 and taking chapter 5 exam. I'll probably give you till Wednesday midnight to work through chapter 5. So because tomorrow we will finish 5.3. So just kind of start working on that homework and let me know if you have any questions, okay? All right, everybody, be careful, be safe, and I will see you tomorrow. Take care. Bye-bye. Bye, everyone.